Hello and welcome to my talk on post-Shannon theory. Today I want to explain you what I'm doing in my research. So I'm the leader of 3 projects at our institute. One project is called post-Shannon theory. There I have one open PhD position. I'm still searching for a good candidate. And I have another project, coding theory and coding methods for new communication models. There I hire 2 postdocs and 2 PhDs. And a third project on quantum information theory, where I hired 1 PhD. All these 3 projects have one thing in common. They're all based on post-Shannon theory. But what is post-Shannon theory? First, if you don't know it, I have to explain to you what is Shannon theory. So Shannon already had in 1948 a nice idea. And on this idea, all our communication is based today. So if you use your mobile phone or if you surf in the internet, always you use this idea of Shannon. And what was his idea? He simplified the communication model. So he looked at the following nice model. Alice wants to transmit a message from 1 to m to Bob. And she can use binary strings of length n to transmit the message over a noisy channel. Because of the noisy channel, Bob receives some word, some binary word of length n. And what is his goal? He wants to find out what was Alice's message. So his goal is really to find out what Alice's message was. More formally, let's look at this diagram. Alice has the message M. XN is a code word Alice is using. Then we have here the noisy channel. YN is a code word Bob received. And then he make an estimate based on his received sequence here, M hat. The question is now, depending on N, what is the largest rate of almost error-free communication from Alice to Bob? And already Shannon gave an answer to this. The message transmission capacity is C. This value depends on the channel, of course. And Shannon showed that one can transmit 2 to the Cn messages. Now, let's come to post-Shannon theory. The first idea of post-Shannon theory comes from Alswede and Deppe. They looked at a very similar model. So Alice has to transmit a message M to Bob. But now what is different? Bob now changed his goal. Instead of asking, what is the message? He only wants to know, is the message M prime? So he's only interested in a message M prime and want to know, have Alice transmitted M prime or not? Of course, Alice has no knowledge on M prime. She only agreed on a coding scheme with Bob. Now what is changed? Of course, you can just use Shannon's approach, and then you can transmit 2 to the NC messages. Now, Alswede and Deppe showed that the identification capacity has the same value. It's also the mutual information depending on the channel. But the surprising result is that the message size increases. So the message size is now 2 to the 2 Cn. So we have a double exponential increase just by changing the goal of Bob. And that was what I want to tell you. So we have the traditional Shannon picture, and here we have a new communication task. And here you see we have a double exponential increase of the message size. This was a more theoretical work. And now in our projects, we always have the goal to make it more feasible, to make it practical, to develop codes for identification, for example, or to make identification robust. That makes perhaps the channel quality change in between. That means robust, or extend this idea to quantum systems. That means to quantum information theory. This was what I want to tell you today. I hope you get an idea what I'm doing, and I thank you for your attention, and if you have questions, please ask now.